All right, guys. Yeah, let's get to it now. So today we're just gonna look at the geometric series. Of course, in our previous lesson, we looked at the concept of logs, and we looked at the important laws, the essential principles that we need to be aware of as far as logarithms are concerned. So I just need you to remember that. I highlighted these two because we often use them. The one that I highlighted here, number one, for example, I said we're going to use this one when even solving problems in the context of geometric sequence or even series. And then the second one, I also told you to watch out for it because it's often used as well in financial mathematics. The third one, you will appreciate it more when we do inverse functions, and when we talk of the inverse of the exponential function, that's where we're going to talk about the logarithm function. And so when we do that switching, when we do that conversion from exponential to logarithm or logarithm to exponential, you will appreciate property number three. So these are very, very important properties which I need you to memorize, know of by heart, whichever way. But I hope you get the message. The point is, you cannot afford to go into an exam not knowing these properties, especially in the consent topics, namely functions, finance, and sequences, as we're doing. Then there are these properties. Again, these properties will play a role again when we deal with functions in particular. So pay attention to these. Make sure now and then, when you know you're going to write a test, maybe on functions and all that, make sure you revise some of this, and you give yourself enough time to even revise questions where you may need to use these. Okay. We have established so far that the general term of a geometric sequence is given by the formula Tn is equal to A times R to the n minus 1. We have established then that A is basically the first term, which is a similar thing, very similar to the to the arithmetic. We saw this with arithmetic again, that T1 is A. Then R is the constant ratio which you get by dividing two consecutive terms. Okay, term 2 divided by term 1, term 3 divided by term 2, and so forth. That is your constant ratio. With the arithmetic sequence, we deal with the constant difference. And of course, we revised the quadratic sequence from grade 11. And we know there we deal with the second constant difference. Okay, then these are just some of the examples we did. So I'll need you to again revise this. Of course, there's a video on this. I'm not going to go over this. What we need to focus on today is the sum of a geometric series. That's what we're going to look at. We have derived a formula for the sum of an arithmetic series. I hope we remember that. And we remember the two versions. There's also a formula, the version where you are given the last term. There's a version where the last term is not known. Again, guys, I will emphasize this, and I'm sorry if I'm wearying you on this, but I have to do this because I know you're students, you forget. And CPF does not work with maths. I hope we are well aware of that. You cannot just say, I'm going to cram pass and forget, because we build on previous concepts here. So whatever type of questions we did with the quadratic and the arithmetic, you may expect similar questions with the geometric sequence as well, or series. So I may not go through exact or same examples with the geometric, but it does not mean you may not get questions on those. Okay, so you need to know how to work out a question in the context of a geometric or arithmetic. Sometimes, especially those simultaneous equations problems, sometimes you get a statement that is in the context of the arithmetic, and then you get a statement that is the context of geometric. And you will need to be able to link those up to be able to solve a problem. So please don't isolate mathematical concepts, okay? In fact, it's a beauty when you can connect mathematical concepts and see how a concept that you learned in arithmetic can be applied in geometry. A concept that you learn in functions can be applied in sequences. So please do not isolate maths concepts. All right, so let's talk about the sum of an arithmetic series. So first of all, we're going to derive the formula. I don't know, I've not thoroughly checked the exam guidelines for this year, but I know this used to be a potential exam question. I've seen it in some past papers where I think trial exams as well. They can either ask you to prove the sum for the formula or derive the formula for the sum of an arithmetic or geometric, but you can confirm with your teachers because you are in different districts and provinces and all that. So you can just confirm with them whether it's important to know this for the exam or not. I know it used to be examinable, but it might not be the case anymore. But in any case, let's show you where it comes from. So remember, for any term in a geometric series, I've got to go A times R to the n minus 1. Standard, right? So I want you to see something. If I want the first term, you see, we have established this already, but we will repeat these things. As you can see, the first term is going to give me A, right? And I want you to see, when I look for the second term, I will get A times R to the 2 minus 1, which will just become A times R. And then if I look for term 3, I'm just substituting into that general formula, I get AR squared. So if you joined that lesson when I was deriving the sum for the arithmetic, you will remember the story of Gauss, right? So check this out. If I have all these terms, I'm sure you can tell what's going to happen now. So if I have all these terms, A plus A times R plus AR squared, doesn't matter whether I write that dot or not. If you like, you may want to include AR cubed, it's up to you. But if I do this and so on and on, what is my last term in any sequence? We know by now that the last term is always Tn. So Tn is A times R to the n minus 1. We know this. Please don't forget that principle. Your last term in any series or sequence is always the general term. So let's call this Sn, just like Gauss did. Let's call this Sn. So that's my sum, right? Now, what we're going to do in the case of geometric, we're going to multiply Sn by R. So I'm going to multiply this sum. So in other words, the equation above, I'm multiplying that by R. Then watch what happens. This becomes AR. This becomes AR squared. This becomes AR cubed. And we will go on and on and on. I'm sure you agree with me. There's going to be AR to the 4 and so forth. Now, I want you to think of what happens when I multiply this last term by R. I want you to think with me there. And I hope you'll agree with me that when I multiply that last term by R, maybe I should do it here. When I multiply A times R to the n minus 1 by an R, law number 1 of exponents say, when bases are the same, you add the exponents. So I will have minus 1 plus 1 there in the exponent. So I'm left with what? A times R to the n. So that's what's left. So when I multiply by R, I need us to all be on the same page that my last term in this instance will actually be, oops, sorry about that. My last term here, looks like I went very far back. Okay, so we should be fine now. My last term will be A times R to the n. Now, maybe let me do this so that you are fully aware of this in your mind. There is a term that comes before AR to the n, by the way, and that term will actually be AR to the n minus 1. Let me just make you aware of that. So there's got to be an AR minus 1 here before this last term of mine, which is AR to the n. Please be aware of that. Where does this come from? Well, it comes from the fact that if I've got an AR there, then I will have an AR in the previous one. So I hope you see this relation. Look at that AR squared. Look at this one here. So surely there is an AR to the 3 somewhere there. And since my last term is AR to the n minus 1, we can see, yes, there it is. That this AR minus, this A times R to the n minus 1 matches the one above. Now, what is the point? Here's the point. I'm going to do some subtraction. So let's call this one equation 1. And let's call this equation 2. So I'm going to do some subtraction here. And in my subtraction, I will do equation 2 minus equation 1. So the left-hand side will become R, the left-hand side will become R times Sn minus Sn. That's what my left-hand side is. And I want you to see now that these terms that I have circled in yellow will actually subtract each other, will eliminate each other. I need you to see that. Now, what's going to be left? Well, I'm going to be left with a negative A, which is basically coming from what? From 0 minus A, because with R times Sn, there is no term that has an A only. There's no term like that. So all like terms are going to eliminate except this A here, except that A. And then with R times Sn, there's no term that matches this one here in the top equation. So that's what's going to be left. I'm going to be left with A times R to the n. Now, I can rewrite this as A times R to the n minus A. And then I hope you do notice on the left-hand side that we have Sn as a common factor. So I can factor out Sn, then I'll be left with R minus 1. In fact, let me factorize in the same step so that, because the left-hand side, the right-hand side can also be factorized. So let's factorize on both sides. So let me factorize this one here so that I have R minus 1 left. And then I factorize out A here. Then I have R to the n minus 1. And then in this instance, I will divide by Sn both sides. So I will have A times R to the n minus 1 divided by R minus 1. And this is the sum, or this is the formula for calculating the sum of a geometric series, okay? With n terms, of course, up to n terms, whereby you would know the total number of terms. But of course, you may expect a reverse question where I ask you how many terms will add up to this much, okay? So that will be the reverse mathematics. Now, whenever there is division, you are dividing by a variable or something like that, I always say, think of your restrictions. And so I hope you note that in this instance, R cannot be 1, because then the denominator becomes 0, and division by 0 is undefined. Even the numerator will become 0 because 1 to any power, 1 to the power n will always be 1. Makes no difference. So we don't want R to be 0. And I hope also you notice that in the normal general form, R cannot be 0 either. Because if R is 0, then Tn is just 0. So what's the point? You're not going to have your geometric series or even a sequence there. So these are the little things that I would like you to actually start paying attention to. There is another alternative form of this, by the way, of this formula. And you would have gotten that if instead of doing equation 2 minus 1, you did equation 1 minus 2. So if you went something like this, if you swapped the order in which I subtracted here, you would get an equation of this form. A into, then you will have 1 minus R to the n over 1 minus R. This is also acceptable. So fortunately in the exam, you get both formulas, right? So you can just choose which one you want to use, it doesn't matter. They both point to the same thing. So this is the main thing, the key thing really that I need you to be aware of. Of course, it is time now to look at illustrations, examples around this geometric series. Okay. So our first example is going to be this one. We are given a geometric series. So fortunately, we are told it's geometric. So the formulas we've got to think of, since it's a series, we've got to think of the general term, Tn is equal to a times r to the n minus 1. And then we've got to think of Sn, the sum of n terms, which we have derived now, a into Rn minus 1, r to the n, my bad, r to the n, okay, not Rn, r to the n, and then that's r minus 1. So those are two formulas for now, at least, which we can think of, right? So now we want to find, number one, how many terms of the series will add up to this. You see now, the question is not that direct one that says, find the sum of the first 10 terms or 13 terms or 20 terms. That's not what it says. Here, it's just, it's the reverse that I was talking about. So I give you the sum. I'm telling you basically here that these terms, 324, 108, 36, etc., have actually added up to this number here. So you got to find now how many of these terms actually added up to this. So we are basically solving for n. So let's quickly find out what is our a and what is our r. I guess we know what a is. So let's note that a is 324. And then for r, we have to do the following. We have to do 108 divided by 324. You can't do 324 divided by 108. At this stage, you are doomed to do that. It's sort of a breakdown. So please don't do that. And again, I'm gonna be a bit unnecessary here. I know you're gonna think I'm insulting your intelligence, but it's fine. If you have to do this, please do it. Do it. Just do it. Okay. You don't want to lose marks over silly things. So if you have to punch in 108 divided by 324, so be it. Okay. So we get a third, right? So that's the value of our ratio. That's the constant ratio. Surely, if you multiply 108 by 1 over 3, you must get a 36. So now we're going to do the following. This, so I have already said it from the previous topic, calculating the sum of an arithmetic series. And we've come across a question like this. So I have Sn, I must find n. So I know that Sn is equal to this all over r minus 1. So these terms have added up to 13,120 all over 27. And then A is 324. It's a Sunday, so I need someone to verify my calculations. Last time I made an error, and then it was spotted after the lesson. So I hope I do have a VAR check somewhere in this room. Okay. Who's gonna check? You see, I'm writing a half instead of a third. So please, I need somebody to be very alert. Okay, cool. So guys, this is what I've got now, right? And I want to show you again, and I'm hoping, I know again, we think differently and all that, but I'm going to try and show you a way which I think, again, this is my opinion, right? A way which I think will help you to minimize the errors. So I know, first of all, students don't love fractions. So the first thing that I would like you to deal with in this situation is this little fraction here, is this thing of a third minus 1. It's going to give us a negative number, of course, all right? Because a third is smaller than 1 for those obvious reasons. So we have to deal with this first. And one of the things you have to avoid, if you have not been told yet, is you must avoid rounding off in between steps. So if you're going to do a calculation while you're still working out something and you get a decimal, instead of rounding off, rather write that decimal as a fraction. Most of the times your decimals, you can write them as fractions. They are rational, in other words. So rather keep it as a fraction, because when you keep it as a fraction, at least one thing you are guaranteed is it is accurate. It has not been rounded off. So I would honestly suggest that you try and keep it like that. All right. So now I'm going to do that third minus 1. If, again, you have to go to your calculator, that's fine. But I think I'm getting a negative 2/3 here in my mind. So my Sunday mind, for that matter. So then let me write it down. So you've got this. So this is 324. I'll try and write it step by step. Of course, these steps are not necessary for some people. So I get minus 2/3, right? Now, you can choose to do this first. You can choose to do that, which I think often creates problems, but you could do it. In other words, you could go to your calculator and say 324, then you could divide it by this negative 2/3. You could do that. You get a minus 486. Okay. And I need you to note that I'm using the division symbol. I'm not using the fraction button, because sometimes what you guys do, you do something like this, right? Fraction over fraction. And then the calculator miscalculates this whole thing. All right. Yes, the 13,120/27 is the sum. That's what the terms are adding up to, Lindy. That's right. So be careful there with your, so rather type it like this. Go 324 divided by negative 2/3, because that's what you're having here in green. So as you can see, I'm getting that negative 486. So what happens now is 13,120/27 is equal to, watch this now, a negative 486 into 1/3 to the n minus 1. So that's what I've got. Now, again, I want to try and avoid distributing. So what I would rather do is to divide by the negative 486. That's what I'm going to do now. So I'm going to take the sum, which is the 13,120/27. I'm going to divide that by the negative 486. And again, watch how I do it. So I'm going to write the sum, and I'm going to divide it by the negative 486 like that. Okay? Then I get this terrifying number, right? It's fine. Let's write it as it is. I think this is what it was. Then on the right-hand side, I'm left with 1/3 to the n minus 1. Let's just verify that number. Maybe let's bring this here. Okay, so we have that. That's what we got, okay? You don't have to worry about how I got that. So we got that. Now, the next thing that we're going to do is, I think you guys call it transposing, but it's basically adding an additive inverse of 1. So on the left-hand side, you end up with the following. You end up with 1 minus 6,560 over 6,561. So this is 1/3 to the n. Now, in your calculator, this is your answer, right? This is what your answer is. I think I'm just going to add 1 to it. So you get 1 over that. Maybe let's bring this as well. Okay. So I just want to do it so that no one will have an issue here. 1 minus Just want you all to see it. Okay, here it is. So now I've got that, right? And chances are 6561 can be expressed as a in terms of base 3. Yeah, basically. Probably it can be expressed by that, but it's up to you how you want to write it. Remember, you've got logs, right? So you can apply your logs and go log. I'm just going for the log method because I want to emphasize the use of logs. So you can do this. Remember what the log rules allows you to do this. Okay. Now, the next thing that we can do is we divide by that. So we have log 1 over that. Look, I'm going to divide this by log of that. And I hope you remember that when we have not written the base, then the base is 10. Okay, so that's very key. So now n is equal to, so we're going to punch this thing as it is. So now log, because the base is 10 already. I hope I'm getting these numbers right. And there we go. We get an 8. So n is equal to 8, which means we do know that the number of terms which will add up to that, which will give us that sum, is 8. So S8 is equal to 13,120 over 27. So that's that. Now, the second one, determine the least number of terms for which the sum of the series will be greater than 485. If you remember this, it's a question that we have done before. What we said when we come to in fact, it's a question that can be asked like this. Let me put it here. It's a question that can be asked like this. So they can ask, find the value of n if Sn is bigger than, so let's see, bigger than what? 485. And I'll say this again. What makes math often difficult is not the fact that you don't know what to do. It's not the fact that you don't know methods to use. It is based on the fact that you don't give yourself enough time to understand the question, to interpret the question. And I think the examiners have realized this, and they often just play with words and they get the better of you. So I guess part of practicing this is exposing yourself to as many past papers as possible, so that you see how different words can have some implications in your solutions. So I will ask again, maybe read a question twice or thrice. And as you read, you are not just reading for the sake of reading. You're actually reading, trying to understand the instruction that is within the question. Okay, so don't just read rushingly and say, oh, I think I know what they want here. And some of you are going to experience this when you write tests and you do corrections and realize, ah, man, I thought I cooked in this test and all that, but the results are opposite. And that will come, you will realize more than half the time, it will come from you reading the question incorrectly. So I want to emphasize this again. Please make sure you read the question. And unfortunately, most of you are going to write in English. Maybe some of you, if you write in Afrikaans and Afrikaans is your home language, you are lucky. But most of you are going to write in English. So unfortunately, you need to have a good understanding of the language. You see, that's how it is. So that's what we are asking. This is the mathematical maybe notation of the question. You see it's asked in simple English here. Determine the least. The word least means small, right? So the smallest number of terms for which the sum of the series will be greater than 485. Okay, so how many terms can you add at the least such that they will add up to a number that is what? Bigger than 485. So I need you to get to that level where by you read a question and you can actually interpret, understand fully what it means. Okay, so give yourself time to read and process. And if it means using a dictionary, use it now. That's how you're gonna learn what words mean, right? That is what is going to help you at the end of the day in your exam. Okay. I just want to say there, I said maths is a language, right? It is reading that's going to help you. So take those English novels seriously, the poems and all that. Try and read that and understand that, because that language aspect, that comprehension aspect of your English subject is actually going to help you in the math as well. Okay. Anyways, enough about it. Enough coaching. Let's get to this now. Okay. Now, if you remember correctly, this is what I said. Whenever we want to find or work out this type of questions, we always first gonna start by trying to figure out actually the exact number of terms that will give me 485. That's what we said. So we would rather find first how many terms are gonna give me 485. So if 6 terms or if adding 7 terms gives me 485, exactly 485, then I know that 8 terms will definitely give me more than 485. If 12 terms will give me the 485, then surely 13 terms will give me something that is bigger than 485. Are you with me? So it's the same thing even if they asked less than. You would always start with the equilibrium part. Where are these equal? Where do I get equality? So that's what we're going to do here. Right. It is still the same series, right? So the value of A has not changed. It is still 324, and the value of R is still a third. So let's note that. So A is still 324. And R is still a third. So now Sn is A times, let's just write this down, the formula, R to the N minus 1, and this is all over R minus 1. So this is 485. So now I'm going to substitute. I'm just going to do my substitution. So 324 into 1 over 3 to the N minus 1. This is basically what I just did with you now, except that there's just a little bit more that we're going to do. So now we know what this is going to give us. We know what this part gives us. Here it is. We know it already. So we know this part is definitely going to produce a negative 486. We know that part. And this is 485. Okay. And then I'm going to divide by this negative 486. So we literally going to have negative 485 over 486. That's going to be the result. And then clearly we got to add a 1 on both sides. So I'm going to have 1 minus 485 over 486 on the right hand side. And that's where my calculator will come into play. So we get something like this. So we get 1 over 486. Now, I'm faced with what? An equation which looks terrifying. But again, as I said, I just want to get you used to using logs. So I'm going to throw in again another law here. And here it comes. 1 over 3 is, n log, I want to apply logs right away, right? N log 1 over 3 is equal to log 1 over 486. So which means n is equal to log 1 over 486 divided by log 1 over 3. That's what it means. So now, let's see what's the result of all this. Log 1 over 486 divided by log of a third. So this is something like 5.63. So now, because you are in your final step, you are literally in your final step, you may round off 5.63. Okay, so we know when dealing with number patterns, whenever we look at the value of n, we expect n to be a natural number, right? So 5 point something. So surely somehow this is basically saying we need more than 5 terms here, because surely 5 terms are not really going to give us exactly 485. Now, if you are in doubt, let's apply the sum formula. So 324, which is my A, into R, which is 1 over 3, to the N, which is a 5, minus 1, close that bracket, over R, which is a third. It's not necessary to do brackets here, but yeah. And then minus 1. So surely we're not going to get 485 when R is 5. In fact, we're getting 484. So your answer, because n must be a natural number, you should say you need to add at least 6 terms. And I want you to see it as I substitute a 6 here, that surely 485.3 is bigger than 485. It might be a small margin as it appears here, but fact is, it is bigger than 485. So you're going to say 6 terms. You need at least 6 terms to get a sum that is bigger than. So your conclusion, 6 terms, or maybe you can write it like this, and there shouldn't be anything wrong with that. You can say S6 will definitely be bigger than 485. You can, instead of writing it out what's in English and then getting tired and all that, you could write it this way and say, look, S6 will be greater, and nothing doubtful about that. What I'd like us to do, I'm going to pause here. No, maybe not, because I just remembered we have to do something now. Let's talk about this concept, because I would like us to really finish the talk on sequences today. Let's talk about this thing called the sum to infinity. It is there as well in infinity. It is there as well when you discuss the geometric series. So I think there's the one little part. Once I've done this, you should be in a position to answer now all questions, not some questions. You should be able to answer all questions in that booklet that I've given you, all questions on sequences and series. So you go to that chapter or that section in the booklet that says sequence and series. Start practicing now. Don't wait for the last minutes. I'm pretty sure if you guys are following the same ATP maybe, and this is what you've covered, you want to be ready for a test on sequences and series, then please do at least 5 to 10 past papers. I know some students do 20 past papers. If you guys wonder how do other students get 90%, 95% and all that, I'm telling you the secret. Some of them do over 20 past papers even. So and that's the basic thing, right? The more you do something, the more you become good at it. Practice makes perfect, right? So they expose themselves to different ways, to the many different ways in which questions are asked, right? And then that's how they're able to get to this. Now, for the sum to infinity, again, this is actually a formula that is being shared. Okay, just give me a minute here, guys. I'm just gonna grab something here. Yes. So now, when it comes to the sum to infinity, right, I want to give you a visual representation of this. In case you are not aware, the geometric series or sequence represents the behavior actually of an exponential function. So if you want to have a picture view of it, you got to just think of an exponential function. Now, an exponential function behaves differently, right? We can have one like this, we can have one like that, like this. In fact, there are arrows on both ends, and we could even have one like this. If I reflect both of these that are above, we could have one like that. Actually want to use different colors here. So let's have this one as blue. So if I reflect the blue, then over the y-axis, by the way, that's what it becomes. And then if I take, well, it could either be the black or the blue. But if I do some reflection, I can get something like this, the green. And then I could get that, the yellow. So these are kind of the different ways in which you could have your exponential graph on the Cartesian plane. Now, if you look at the blue and the yellow, these are what we call diverging graphs. They show a pattern that is kind of diverging. So which means it is either going hugely large, it goes just large, goes on and on and on, bigger, bigger, bigger. Remember, your y-axis is what tells you whether you are increasing or decreasing. So as you read upwards the y-axis, you are definitely increasing. As you read downwards the y-axis, you are definitely decreasing. So if you look at the blue, remember we read, our direction of reading is from left to right. So when you look at the blue and you are reading the blue graph from left to right, you should be seeing that surely the blue graph is going infinitely bigger, right? But when you look at the yellow one, it is going infinitely small, very small, because you are reaching extremely small negative numbers. If you look at the yellow one, it keeps on going down, 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 down. It doesn't increase. All right. And this again, where you get asked a question, is a function increasing or decreasing? In the simplest way, as if you, those of you who remember the Slopeman test, I didn't talk about it here, but you'll remember that is increasing, that is decreasing. So again, that's it. But then you look at the black graph, right, and the green graph. One thing about those two graphs is that they are actually decreasing, because as you read from left to right, what is happening? The y values are going down. Surely the y value here is bigger than the y value there. You see what I'm talking about? I don't know if you see what I'm talking about. Okay, so that is the first thing. Oh, by the way, the green is actually increasing as well, but I will show you something special about it. While it is increasing, it is bounded, it reaches a limit. Okay, so the black is surely decreasing, right? The black is definitely decreasing, no doubt about that. But as it decreases, those of you who remember the asymptote theory, the x-axis sort of acts as an asymptote. It acts as a boundary. And what actually that means is that it is a limit. You know, speed limit. Of course, not everyone follows the speed limit, but this black graph is actually limited in a sense that it will never cross the x-axis. It will never touch the x-axis. It will only keep coming closer and closer and closer to the x-axis. So that's the first thing that we need to note. We have geometric series that behave like that. We have geometric series where you will see, but this series is decreasing, decreasing, decreasing. But you will notice that as it decreases, now the sum, as you calculate the sum, so sometimes you realize the sum to 100, the sum to 150 terms, you're going to realize that, but these sums are just approaching the same number. They don't seem, this, as you calculate the sum does not seem to go beyond a certain number. Maybe you are calculating it and you get 285 point, maybe 01. And then the next one, you get 285.001, something of that nature. This is the situation that I'm trying to explain to you here. All right. The bottom line is 285 seems to be the number that is the ceiling, that is the limit for that sum. Now, that is exactly what is happening also with the green. The green, although it is increasing, yes, surely this number here on the y-axis is smaller than that number on the y-axis. But what happens is it gets closer to the x-axis, and the x-axis acts as a boundary, as a ceiling. So it's never going to go beyond the x-axis. So series that are represented by the black and the green are referred to as convergent series. They converge, they reach a certain point where no matter the number of terms you're adding up, you're never gonna exceed a certain number. That is the whole point. So please take note of that. Very, very crucial. So these are convergent. Now, there is a condition for convergence. Whenever you want to know whether a series converges or not, then the value of R will tell you that, actually. The value of R will tell you that. You will notice for any convergent series that the value of R is somewhere between a -1 and a 1. That's what you're going to notice. The value of R is somewhere between a -1 and a 1. Now, once a series is convergent, you can always calculate its sum to infinity. And the sum to infinity, this is also given in the information sheet. The formula goes A over 1 minus R. Once again, I remind you, you must have made sure or established at least that the value of R is somewhere between -1 and 1. And there are many applications, by the way, to the sum to infinity. There are many awesome examples that we can look at, actually. And I think I want to take about 3 examples or so, and then maybe I'll let you go after that. So let's have a look at those 3 examples. If you want to do a leg stretch for 2 minutes or go grab a glass of water, you are welcome to do this. I'll literally wait for 2 minutes. All right, you should all be back now. Let's look at our last few examples, and then we close the day. The first example here on the sum to infinity is basically requiring us to calculate that sum, and this is a geometric series. So we know the formula says S infinity, or the sum to infinity, is equal to A over 1 minus R. Now let's just check if indeed R is between -1 and 1. A is obviously a 2, but to find R, remember you're going to have a -4 over 3, and you're going to divide that by a 2. Okay, so you can use your calculator for this. I'm just going to try and do a quick math here. So I get a -2 over 3, and that seems to be well within the jurisdiction. Or is it -2 over 3? I suppose. Now, the next thing that I'm going to do, I'm going to substitute. Therefore, the sum to infinity is A is a 2, 1 minus, watch out, you are subtracting a -2 over 3. And then you want to do this in your calculator. So you're going to go 2 divided by, then you're going to go 1. It's basically plus 2 over 3 now, because that whole thing changes. And I'm getting a 6 over 5. So this is a 6 over 5. So the sum to infinity, 6 over 5. So in other words, it doesn't matter how many terms you're going to add, you're going to realize that those sums keep on just, they can't seem to go beyond that 6 over 5. That is what we have here. Right. Another one, classical one, solve for x. we are given a series in terms of x, and we are asked for which values of x will the series converge. We know if a series is going to converge, then the ratio must be between -1 and 1, right? So we need to find the ratio in terms of x. So remember, by definition, the ratio will be T2 divided by T1. And if you don't like doing T2 divided by T1, you can do T3 divided by T2. But the bottom line is that this ratio will be 3x into x minus 2, and we got to divide this by 3x. Surely, we're going to be left with x minus 2. So we are now faced with a situation where we are solving for x in the inequality x minus 2 between 1 and -1, right? Or -1 and 1. That's what we're faced with here. Now, all we're going to do now is, I think there's a grade 10 concept. It is actually where you do linear inequalities. And I hope you are seeing this. I'm pausing just here to show you that it is important to remember the concepts you learned in your earlier grades. So I'm going to add 2 both sides. When I do that, I get x is between 1 and a 3. So any value of x that is between 1 and 3 will actually have this series converge. B, if x is a value for which the series converges, calculate the sum to infinity of this in terms of, listen to this, and I think this is the one thing that will clear the confusion if there was any confusion in terms of x. So in other words, just go there into the formula and substitute your terms in terms of x. In any case, they were given in terms of x. So you got the ratio in terms of x. Then this is 1. I want you to see again, I've emphasized this. See again how brackets are going to save you here. If you substituted this x minus 2 without brackets, you are doomed. So I hope you see again why it is a good practice to always have brackets when or use brackets when substituting. And that's it. Your sum to infinity here is 3x over a 3 minus x. Just a little note as I close off here, I have taught sigma notation. You can check the previous lessons that they are there on YouTube. Just a little note. In the case of the sum to infinity, if, in other words, you are given a sum to infinity in terms of sigma notation, I want you to be aware of the fact that this is what would happen in such a situation. You would have your sigma notation sign, but there will be an infinity at the top. So when I give you something like this, you must know they are basically saying you are dealing with a sum to infinity. So you are evaluating a sum to infinity in this case. And so what you will need, remember, the formula for the sum to infinity tells you need A, you need to know your first term in other words, and you need an R. So you need to know your constant ratio. So it's going to be very important here that you actually at least write out the first 3 terms so that you can know what A is and you can know what R is. So you will substitute 3 to the minus 1 plus, and then 10 times 2 to the 3 minus 2. Where do I get all this? Remember, k, you started at 1, and then after 1, you increment in ones, so you go to 2, and then your last one here will be 2 to the 3 minus 3, and so on, right? So this whole thing is, I think 3 minus 1 is a 2, 2 squared is a 4, and that will be a 40. This one will be a 20, and this one will be a 10. And so when you continue with this, it turns out that A is 40 and R is a half, because you're going to go 20 divided by 40, which is a 2 over 4, and that is basically a half. So now you know this. That means the sum to infinity is 40 over 1 minus a half. 1 minus a half is a half. 40 divided by half, 40 divided by half is equivalent to multiplying that 40 by 2. So the sum to infinity here is pretty much an 80. So that's how you would have worked this one out here. So very, very important that you also know the link between sum to infinity and sigma notation. The same thing with, excuse me, the sum of a geometric series. You need to be able to do that. You need to be able to figure all that out. And I think maybe when we meet in our next session, we will just do sort of a summary or an overview of what we have discussed so far. Maybe just do weird questions or questions that seem difficult so that you can have a sense, a feel of how things can be advanced here. Maybe we'll do that. I think that will actually wrap it up nicely rather than leaving it here. So yeah, that's about it for today. Go to that past paper booklet. Do your best to attempt every question that is being asked on sequences and series, and we'll see how to help you. Okay, that's about it for today. Cheers, guys. Have a good week.